Machine learning, these are some of the hot topics anywhere around the world. Mirror image of what the other part is. So how we orient, keep the genome in alignment also matters quite a lot. And so by putting it this way, if we want to compare a 1 and 2 genome, we can just put it one after the other. But if we want to compare cells with cells and cells with non-cells, then how you keep them also matters quite a lot. And usually what happens is that as the sequences sizes increases, the time complexity, the big O in nomenclature in computer science algorithms, that can actually take exponential time. And if you do it cleverly, like you take the memory component in such a way that then you, with the increase in the amount, the load, the time that it takes increases linearly instead of going exponentially. And that is one of the advantages of this method or this tool. And needless to mention that one core will take this much amount of time, and if you go into multi-core processor, then there is a significant drop in the time that it takes. And this is what we are doing for, this is being done for parallel computing, where you have one problem, we have multiple computing cores, the same problem is being solved by multiple cores. We have moved into GPU computing, and there we have like millions or several thousands of cores, and this can actually be done much quicker. To give you a taste of how beneficial it is, so if we use just one computing core, it can take this much amount of time, and if we just increase the number of cores to 4, the time does not reduce 4 times, but it reduces far more times, maybe 20 times or less. And that is because it's not just about the computation, there are also bottlenecks in the whole pipeline or in the whole process. There are bottlenecks, and if you encounter such a bottleneck, then usually the time goes up really up. And that's the advantage, other than the cache benefit that you have. The cache hits also increases by the number, such as the gene, and it does it in parallel. So now I talk about more about application of this tool, for which I published a paper called Customized Biomedical Informatics, and later on I also published a paper called The Unmasking of Mitochondrial Atom, because previously what was known was a paper called Mitochondrial Eve, as it is known that the mitochondrial DNA passes from the female to the offspring. But there were certain cases that there could be leakage, and the mitochondrial DNA can pass from the paternal line as well. And this was my second such discovery. The second scientist saying that there could be a possibility of the mitochondria to pass from the man to the offspring. And usually what is done is that you look for the variations in the genome architecture. It could be a single nucleotide polymorphism or variations, as you might want to call it, or it could be larger variations such as insertion deletions, inversions, copy number variations, intra or interchromosomal, and there could be novel sequences which could be truly novel if it doesn't match any known publicly available databases, and so on. And a variation of the GMSet software tool that I talked is called the Genome Break, which I made. And here, instead of plotting the whole matrix, here is a reference genome, say human reference genome, build 17, and here it is your assembled genome, right? You can do the assembly of the genome using standard tools like Abhishek or so. And then you look for as high identity as possible. Say if you go to 100% or more than 95%, then we get more or less a diagonal line, and there could be, and if we want medicine that we propose, so gene co-expression, linkage disequilibrium, and then functional annotation. So it's essentially a pipeline. We first detect the community, then we look for linkage disequilibrium, and then the functional annotation, all packed using graph algorithm, particularly the community detection algorithms. There are standard algorithms like Gilbert-Newman algorithm and a couple more algorithms. I didn't make those algorithms, I implemented them. And once you have that, what you actually do is that, so I assume everybody knows what graph is. Graph is like you have different vertices or different points, and you draw a line, there is a relation between them. For example, if a gene is being overexpressed or expressed, less expressed by a SNP, then we connect a line between them, as you can see in this diagram. So you know about ensemble. So here's the ensemble. You have like 3 genes over here, and you have, these are the different variations. And the nomenclature is that we start with the chromosome number, then the position, and then what is there at the reference genome. Maybe in Arabidopsis you have C over there, and then if you have a different strain of Arabidopsis, which you have sequenced and assembled and then mapped, then you have C replaced by T, and then you also mentioned the version of the genome that was used for mapping or comparison. So this is essentially a nomenclature, and then all the connecting lines to these 3 genes are essentially saying whether they are upregulating the gene expression or downregulating. You know, the levels of expression of a gene depends on more regions in the genome, such as enhancers and more regulatory domains. So this is what we call as a community. So this essentially makes a community that these 3 genes are having a common set of variations that are, having an effect on it. And out of these variations, some might be the positive one, and some might be spurious variations. They might not be really having an impact. And how we determine that is by linkage test equilibrium. I will talk about it in a minute. But before that, how we do it is that we put